On July 12, 2022, NASA released a photograph. It showed a patch of sky roughly the size of a grain of sand held at arm's length. And inside that grain of sand, thousands of galaxies. Ancient light, collected by a mirror the width of a school bus, suspended 1,000,000 miles from Earth. Scientists had been preparing for this image for years. The James Webb Space Telescope had cost $10 billion and 3 decades of work to put into orbit. And the researchers who had designed its instruments, calibrated its sensors, and spent careers waiting for this data. They knew what the early universe was supposed to look like. They were wrong. What the James Webb data actually showed, in that first image and in every deep field observation that followed, was a universe that had organized itself too fast, too completely, and too early for our best models of physics to explain. Not marginally, not by a factor that could be cleaned up with better calibration or more precise measurements, by a factor of 10. For the next hour, we're going to go through that data carefully. What it shows, what it contradicts, what the scientific community has said about it, and what it means that the most powerful telescope in human history looked at the early universe and found something our models say should not be there. This is a full documentary examination of the James Webb Impossible Galaxies problem, and everything it has surfaced beneath it. Let's start with the model it broke. Before we can understand what Webb found, we need to understand what Webb was supposed to find. And for that, we need to understand the framework that governed cosmology for decades before that first image arrived. It is called the Lambda Cold Dark Matter model. Most cosmologists refer to it simply as Lambda CDM, and for 40 years, it was one of the most successful predictive frameworks in the history of science. Here is what it tells us. 13.8 billion years ago, the universe began. In the first fraction of a second, space itself expanded at a rate that still defies intuitive description. Within the first 3 minutes, the fundamental particles that would eventually become atoms had formed. For the next 380,000 years, the universe was a hot, opaque plasma, a fog so dense that even light could not travel freely through it. Then the fog cleared. The universe cooled enough for electrons to bind to protons. Atoms formed. Light flooded through for the first time. That ancient light is still detectable today as the cosmic microwave background, a faint glow that fills the entire sky, carrying in its temperature patterns a detailed record of what the universe looked like at that first moment of transparency. What came after that moment, according to Lambda CDM, was a slow and grinding process. Gravity took hold of tiny variations in density, fluctuations smaller than 100,000th of a degree across that ancient light. Gas clouds began to collapse. The first stars ignited somewhere around 200 million years after the Big Bang, small, hot, and short-lived. Those stars died, seeded the surrounding gas with heavier elements, and over hundreds of millions of years, gravity pulled those clouds into the first primitive galaxies. The key word in that process is slowly. Galaxy formation, according to Lambda CDM, was supposed to be a generational project. The universe needed time, billions of years, to build the infrastructure required for massive, structured, stable galaxies. Dark matter halos had to form first, providing the gravitational scaffolding. Ordinary matter had to fall into those halos, cool, and condense. Stars had to form, evolve, and die, recycling material into the next generation. And galaxies had to collide and merge repeatedly before they could reach the mass and structural complexity we observe in the universe today. This framework wasn't just a theory on a whiteboard. It was tested against decades of observation with every major telescope humanity had ever built. Hubble, the Very Large Telescope, ALMA, Spitzer. In every instance, what we found matched what Lambda CDM predicted, within the expected margins. The cosmic microwave background matched the model's predictions with extraordinary precision. The large-scale structure of the universe, the filaments, voids, and galaxy clusters that form the cosmic web, matched the simulations. By the time Webb launched in December 2021, Lambda CDM wasn't just the leading cosmological model. It was, for most working astronomers, the established description of reality. If this kind of deep investigation is what you come here for, the like button helps this reach more people who'd want to spend an hour on this. Webb was designed, in part, as a final precision test of that description. By observing the universe as it was in the first few 100 million years after the Big Bang, earlier and deeper than any previous instrument could reach, it would confirm the early stages of the slow process Lambda CDM described. The first dim proto-galaxies, the messy, chaotic raw material of what would eventually become the universe we see today. The fog. Lambda CDM was specific about what that fog should look like. Small structures, gradual coalescence, no large stable galaxies, no organized spiral arms, nothing mature or massive until the universe had had billions of years to build it. Webb looked into the fog. The fog was supposed to last for hundreds of millions of years. Webb looked into it and found cities, not metaphorically, fully formed structures, massive, luminous, organized, galaxies that looked, by every measurement available, like galaxies that had been growing for billions of years, in an era when billions of years had not yet passed. The specific data we're about to examine is not a single anomaly, a single outlier, or the product of a single observation. It is a pattern that has now been replicated across multiple surveys, multiple instruments, and multiple independent research teams. And understanding exactly what that pattern shows, and exactly why it shouldn't exist under the model that governed cosmology before Webb, is where this investigation has to begin. In February 2023, a team of researchers published a paper in the journal Nature. The lead author was Ivo Labbé of Swinburne University of Technology in Australia. The co-authors included Erica Nelson, an astrophysicist at the University of Colorado Boulder. The paper described 6 objects that Webb's infrared cameras had detected in a patch of sky previously imaged by Hubble. Hubble had seen nothing remarkable in that region. Webb saw something different. Each of the 6 objects appeared to date back to within 500 to 700 million years of the Big Bang. And each of them was massive, containing hundreds of billions of stars. Numbers comparable to the Milky Way today, a galaxy that has had 13 billion years to accumulate that mass. Nelson's documented reaction, published alongside the paper's release, was direct. You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. That phrase, "should not have had time," is not dramatic language. It is a precise technical statement. Under Lambda CDM, the formation of a galaxy with hundreds of billions of solar masses requires a specific sequence of physical events, each of which takes time. Dark matter halos have to grow through mergers and accretion. Gas has to cool and collapse inside those halos. Multiple generations of stars have to live and die. The mathematical constraints on how quickly that sequence can proceed are not arbitrary. They are derived from the measured laws of physics, the speed of gravity, the density of matter in the early universe, the rate at which gas clouds cool. And when researchers compared the observed mass of these 6 galaxies against what Lambda CDM's best simulations predicted should exist at that epoch, they found something the published paper described as in tension with standard models. That phrase is careful scientific language. Here is what it means in plain terms. The total stellar mass observed in these galaxies was roughly 10 times higher than the maximum amount Lambda CDM simulations predicted could exist at that point in cosmic history. 10 times, not 10%, not double. 10 times the maximum the model said was possible. The team ran the analysis again. The second result was the same as the first. This is not a small calibration error. It is not an instrument artifact that better data would erase. In the months following that initial publication, the observation was replicated. Webb found more of these objects, not fewer. The pattern held. To understand why this number matters, consider what it means structurally. Lambda CDM isn't a rough sketch. It is a precisely calibrated model with measured parameters. When you run its simulations on the best supercomputers available, it produces a specific prediction for how much stellar mass should exist at any given point in cosmic history, with error bars that the scientific community considers well understood. Exceeding those predictions by 10 times isn't a finding that sits comfortably inside those error bars. It's a finding that sits entirely outside them, in a region of parameter space that the model says should be physically inaccessible. Here is a way to feel what that means. Imagine you are a geologist examining a canyon. You know the rate at which water erodes rock. You know the composition of the stone. Based on those measurements, you calculate that this canyon should have taken 3 million years to form. Then you find artifacts at the bottom that are only 10,000 years old. You don't immediately conclude that your understanding of geology is wrong. You check your instruments. You look for alternative explanations. Maybe the dating is off. Maybe there was a catastrophic flood that doesn't fit the standard erosion model. But if 10 different geologists run 10 independent analyses and they all return the same result, the canyon is 10,000 years old, and the standard model says that's impossible. You are no longer looking at a measurement error. You are looking at a problem with the model. What researchers began exploring after that February 2023 paper were the possible mechanisms that could have accelerated early galaxy formation beyond the predicted limits. One proposal: bursty star formation. The idea that rather than forming stars at a steady rate, early galaxies may have formed them in sudden, intense bursts, with long periods of relative quiet between them. This would make them appear brighter and more massive in snapshots than they actually are on average. A 2023 study from Northwestern University, published the same year, ran simulations incorporating bursty star formation and found it could partially account for the observed brightness. Partially, not fully. And brightness alone does not explain the mass measurements, which are derived from spectroscopic analysis, a separate technique with its own set of verification steps. There was also a second piece of data embedded in Webb's early observations that was noted by several teams, and then, in most public discussions, quietly set aside. We're going to note it here and hold on to it. In several of the galaxies Webb photographed from this era, researchers detected higher levels of heavy elements than models predicted should exist at that age. Not marginally higher, significantly higher. Elements that, according to standard stellar evolution models, require multiple generations of stellar birth and death to produce. Generations that, at 500 million years after the Big Bang, there hadn't been enough time to complete. We'll return to that detail. Because in the context of what Chapter 5 examines, it means something different than it appears to mean right now. For the moment, what we have established is this. Webb found galaxies in the early universe that are too massive, too structured, and too chemically complex for the timeline Lambda CDM describes. The evidence is confirmed, the explanation is not, and what Webb found next, in a single galaxy, made the problem considerably more urgent. At the beginning of this documentary, I said we were going to look at every layer of what Webb found, not just the headline, but what the data actually shows and why it matters. We've looked at the first layer, galaxies that formed too fast in a universe that should have been too young to produce them. What Chapter 3 shows is why that layer is not enough on its own, and why a single galaxy, confirmed by Webb in 2023, changed the nature of the conversation. This is the part of the investigation that moves the anomaly from interesting to genuinely difficult to explain away. The deep dive into what this data actually shows starts now. There is a specific type of galaxy in astronomy called a quiescent galaxy. The term means what it sounds like, a galaxy that has stopped forming new stars. The gas and dust that fuel star birth have been used up or expelled, or both. The galaxy is coasting on the light of the stars it already made, gradually fading over billions of years as those stars age and die. Quiescent galaxies are common in the universe today. We see them everywhere in the nearby cosmos. What makes them notable is how they became quiescent, the process by which a galaxy's star formation shuts down, which astronomers call quenching. In 2023, a team using Webb's NIR-SPEC spectrograph published a detailed analysis of a quiescent galaxy cataloged as GS9209. The lead author was Kate Whitaker of the University of Massachusetts Amherst. The paper appeared in the journal Nature. GS9209 is not unusual in its shape or its appearance. What is unusual is when it became quiescent, and how quickly it got there. The spectroscopic data from Webb shows that GS9209 formed the vast majority of its stars within a window of roughly 800 million years. That's already fast by the standards of modern galaxy formation theory. But the timing is what makes this observation significant. That 800 million year formation window ended, and the galaxy went fully quiescent within the first 1.8 billion years after the Big Bang. Let's be precise about what that means. Our own Milky Way began forming roughly 13 billion years ago. It is still forming stars today. It will continue forming stars for billions of years more. Star formation in the Milky Way has been an active, ongoing process across virtually the entire history of the universe. GS9209 was born, built hundreds of billions of stars, and went completely dark before the universe was 2 billion years old. It formed, it burned, it died, before most galaxies had started. The scientific response to this data was careful but unambiguous. Whitaker's paper described the galaxy as presenting a significant challenge to our understanding of how galaxies form and evolve. In a published interview, she noted that the existence of GS9209 at this epoch pushes the boundaries of what we thought was possible. What makes GS9209 more than an outlier is the quenching mechanism. Dead galaxies don't just stop forming stars by accident. Something causes the fuel supply to be cut off. The most widely accepted explanation involves the supermassive black hole at the galaxy's center. When that black hole feeds aggressively on surrounding gas, it releases so much energy that the gas is expelled from the galaxy entirely, shutting off star formation. This process is called AGN feedback, or active galactic nucleus feedback. The problem is timing. For AGN feedback to quench a galaxy within 1.8 billion years of the Big Bang, the black hole at GS9209 center would have needed to grow to supermassive scale, billions of solar masses, extraordinarily quickly. And that growth itself requires a process we don't fully understand. Here is the binary that emerges from the data on GS9209. Either the process of black hole growth and AGN feedback can proceed far faster in the early universe than our current models allow, which would require revising our understanding of early black hole formation, or something else caused this galaxy to shut down so rapidly, something that our models don't yet account for. The data doesn't cleanly favor one over the other. Both options require departing from the standard picture. And here is where the investigation becomes more complicated. Because GS9209 is not alone. Webb has now observed multiple quiescent galaxies from this early epoch. Not one, not two, a pattern. Massive galaxies that formed quickly, lived briefly, and went dark in an era when our models say they should barely have begun. This matters because a single anomaly can always be explained as a statistical outlier. Physics produces edge cases, but a pattern of outliers is a different category of problem. A pattern suggests that whatever mechanism produced these galaxies, whatever accelerated their formation and then shut it off, was not rare. It was, in some sense, the norm in the early universe. And if it was the norm, then our standard account of how the early universe operated is missing something substantial. That missing thing might be in the physics of black hole formation. It might be in the physics of dark matter halo growth. It might be in our understanding of how gas behaves in an environment far denser and hotter than anything that exists in the universe today. Or it might be in something deeper, something that reaches into the foundations of the model itself. We haven't gotten there yet, but in Chapter 4, there is a second independent data set that measures something entirely different and arrives at a conclusion that is in direct mathematical conflict with the first. Everything we've examined so far has involved the early universe, observations of objects that existed in the first 1 to 2 billion years after the Big Bang. The anomalies are real and confirmed, but they live in a corner of cosmic history that is, by definition, hard to reach and hard to verify. What I want to examine now is a problem that operates in a different domain entirely. One that involves measuring the present-day universe and the well-understood nearby cosmos. And it produces a result that is, if anything, more unsettling than the early galaxy data. It is called the Hubble Tension, and it has been the most significant unresolved problem in observational cosmology for over a decade. Here is the background. In 1929, Edwin Hubble established that the universe is expanding, that galaxies are moving away from us in every direction, and that more distant galaxies are receding faster than nearby ones. The rate of that expansion is described by a number called the Hubble constant, measured in kilometers per second per megaparsec, essentially how fast 2 points in space are moving apart for every unit of distance between them. Getting that number right is foundational. It sets the scale for everything. The age of the universe, its size, the rate at which its expansion is accelerating, and ultimately, its fate. For decades, 2 primary methods existed to measure the Hubble constant. They use completely independent techniques. They access different epochs of cosmic history, and they have been refined by separate teams with separate instruments across separate decades. The first method analyzes the cosmic microwave background, that ancient light from 380,000 years after the Big Bang. Using Lambda CDM as the interpretive framework, researchers calculate what the expansion rate should be today based on the conditions measured in that early light. The Planck satellite, which mapped the cosmic microwave background with extraordinary precision, produced a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second method measures the expansion rate directly in the nearby universe. Researchers use a class of exploding stars called Type Ia supernovae as distance markers, standard candles whose intrinsic brightness is known, so their apparent brightness tells us how far away they are. By measuring both their distance and their recession velocity, researchers calculate the expansion rate empirically. The S80ES collaboration, using Hubble Space Telescope data refined over years, produced a Hubble constant of approximately 73 kilometers per second per megaparsec. Those two numbers disagree by approximately 9%. In everyday life, 9% sounds manageable. In fundamental cosmology, where these measurements represent the best precision humanity has ever achieved on a single quantity, and where both methods have been checked, cross-checked, and independently replicated by multiple teams, 9% is not a rounding error. The gap between those two measurements is called the Hubble Tension, and it is real. It has been confirmed by multiple independent analyses using multiple independent methods. Both sides have been exhaustively reviewed for systematic errors. The instruments have been checked. The calculations have been verified. Both measurements are right, and they disagree. The gap between those two measurements isn't an abstraction. It is a disagreement about the age, size, and future of everything that exists, including the chair you're sitting in right now. The logical consequence of two rigorous confirmed measurements of the same quantity giving different answers is precisely stated. Either our model of the early universe is wrong, or our understanding of how the universe evolved from that early state to today is wrong. There is no third option that preserves both measurements and leaves the standard model intact. Now here is where Webb enters this second problem. One of Webb's primary missions was to provide new, sharper measurements of those type Ia supernovae, the distance markers used in the second method. With Webb's infrared sensitivity and its dramatically improved resolution, researchers expected to either confirm the tension or find the systematic error that had been causing the discrepancy. The results were published in 2024 by the SH0ES team. Webb's measurements confirmed the supernova distances with greater precision than Hubble had achieved. The analysis was thorough. The data was clean. The tension did not go away. If anything, the improved precision made it harder to attribute to instrument artifacts. The two measurements still disagree by approximately the same amount. The gap is real, and Webb, the instrument designed to resolve it, did not resolve it. So we now have two independent categories of evidence, collected by different instruments, using different techniques, studying different epochs of cosmic history. And both of them are pointing toward the same uncomfortable conclusion. Lambda CDM, the model that successfully described the universe for 40 years, is under structural pressure. Not in the sense of minor calibration adjustments, in the sense of fundamental assumptions that may need to be revisited. The early galaxy data says the universe built massive structures far faster than the model allows. The Hubble tension says the universe is expanding at a rate that two independent methods cannot agree on, and the disagreement is too large and too well confirmed to be measurement error. Two different probes, two different anomalies, one model that cannot comfortably accommodate either of them. The question is no longer what specific galaxy or measurement doesn't fit. The question is what it means that so many things don't fit simultaneously. Chapter 5 is where the full weight of that question arrives, because there is a third layer to this investigation, one that connects the early galaxy data and the Hubble tension through a single question that reaches into the foundations of the model itself. And it concerns something that makes up 27% of everything in the universe, something we have never directly detected, and something that Webb's findings have put under a new kind of pressure. We've now examined three independent data sets: early galaxy masses that exceed the model's predictions by a factor of 10, a dead galaxy that completed its entire life cycle before the universe reached 2 billion years old, and a measurement of the universe's expansion rate that, from two rigorously confirmed independent methods, gives two irreconcilable answers. Each one, on its own, could be a puzzle waiting for a technical solution, but together they form a pattern. Everything established in the last 35 minutes becomes the foundation for the question that Chapter 5 examines. It's not just about what the data shows, it's about what it means. For the architecture of the model, for the physics underneath it, and for the possibility that the universe we thought we understood is not, in some fundamental way, the universe we actually live in. The data in the next chapter, the complete breakdown of what these anomalies imply when they are examined together, is honestly the reason this documentary exists. To understand the full weight of what Webb has uncovered, we need to understand what dark matter actually does in the standard model. And, well, why the early galaxy data creates a problem that doesn't just challenge our observations, but challenges the scaffolding on which those observations are built. Dark matter is not a fringe idea. It's actually one of the most tested inferences in astrophysics. The evidence for it comes from galaxy rotation curves. You know, the observation that stars at the outer edges of galaxies rotate at speeds that their visible mass just can't explain. Then there's gravitational lensing, the way massive galaxy clusters bend light in ways that require far more mass than we can actually see. There's also evidence from the large-scale structure of the cosmic web and from the precise patterns in the cosmic microwave background. Every independent line of evidence points to the same conclusion. Roughly 27% of the total energy content of the universe is dark matter, mass that interacts gravitationally but does not emit, absorb, or reflect light. In Lambda CDM, dark matter plays a specific and indispensable role in galaxy formation. It forms halos, these vast spherical clouds of gravitational influence that act as the seeds around which ordinary matter gathers. Gas falls into these halos, cools, and eventually becomes stars. The dark matter halo is the foundation. The galaxy is what gets built on top of it. And here is the critical constraint that Webb's early galaxy data runs directly into. Dark matter halos don't appear fully formed. They grow through a hierarchical process. Small halos form first, then merge into larger ones over time. The rate at which they can grow is governed by the same laws of physics that govern everything else. Gravity, the expansion of space, the density of matter in the early universe. Lambda CDM makes a specific prediction about how large a dark matter halo can be at any given point in cosmic history. And for the most massive of the galaxies Webb has observed in the early universe, objects containing hundreds of billions of solar masses, the dark matter halo required to host them should not yet have existed. The scaffolding shouldn't be there, but the building is standing. There are three serious theoretical responses to this problem currently being pursued in the literature. The first is that dark matter halos in the very early universe formed more efficiently than our simulations predict. Perhaps because conditions immediately after the Big Bang allowed for faster clumping of dark matter than the standard model accounts for. This is the most conservative proposal. It requires adjusting the simulations, not the underlying physics. The second is, well, a bit more radical, that dark matter itself behaved differently in the high-temperature, high-density environment of the early universe. Some researchers have actually proposed that dark matter may have had different interaction properties at high energies, properties that would have allowed it to cluster more rapidly and form larger halos earlier. If that's the case, then, our simulations of the early universe are using the wrong physics for the wrong environment. The third option is the one most researchers are honestly least comfortable with. But it's the one that the combined weight of the anomalies keeps pressing toward. I want to be careful here, because after spending a long time with this data, the honest thing I can tell you is that I don't have a framework for what it would mean if the answer turns out to be the third option. I'm not sure anyone does. The third option is this: dark matter is not what we think it is. Not in a conspiratorial sense, but in the sense that the entity our models describe as dark matter may be a first-order approximation of something more complex, more varied, or more dynamic than a simple gravitational scaffold. This connects to something that was mentioned earlier in this investigation, the detail we flagged in Chapter 2 and set aside. The elevated levels of heavy elements detected in early galaxies. Elements that require multiple stellar generations to produce. If those heavy elements are real, and the spectroscopic data strongly suggests they are, then either the very first stars were far more massive, more numerous, and more efficient at producing heavy elements than our models estimate. Or those elements were produced in an environment where the physics of stellar evolution operated differently than it does today. Both possibilities point toward the same question. Were the conditions of the very early universe, the physics, the densities, the temperatures, the properties of matter itself, sufficiently different from the present-day universe that our models, built from measurements of the present, may be systematically miscalibrated for that era? And there is one more piece of evidence that connects to this question, one that is not about galaxies, not about expansion rates, but about something even more fundamental. There is a number in physics called the fine structure constant. It governs the strength of the electromagnetic force, the force that determines how atoms absorb and emit light. Every spectral line we use to measure the composition, temperature, and velocity of distant objects depends on this constant having a specific value. It is assumed to be exactly the same everywhere in the universe and throughout all of cosmic time. The laws of physics are universal. That is the bedrock assumption on which all of observational astronomy is built. Several independent research groups, analyzing the spectral lines of quasars across a range of distances and look-back times, have detected hints, not confirmed detections, but statistically significant hints, that the fine structure constant may have been slightly different in the early universe than it is today. The variation, if real, is small, less than 1%. But if fundamental constants vary across cosmic time, if the laws of physics as we measure them today are not identical to the laws that governed the early universe, then every prediction our models make about the early universe is built on a foundation that may not apply. And as of this recording, that question has no confirmed answer. Either our models of the early universe are fundamentally incomplete, constructed from physical laws measured in the present and assumed to be valid in the past, or something happened in the first billion years of cosmic history that we are only beginning to have the instruments to detect. The James Webb data on impossible galaxies is not, in the end, just about galaxies. It is about the validity of the framework we use to understand everything the universe has ever done. That is the weight of the anomaly. And in Chapter 6, we're going to take a careful inventory of exactly what the evidence confirms, and exactly what it leaves open. After 50 minutes of evidence, what does the data actually establish? Let's be precise. Not about what seems likely, not about what the anomalies suggest, but about what the observations have directly confirmed. Webb has confirmed the existence of massive, structurally complex galaxies in the first 500 to 800 million years after the Big Bang. These detections have been validated through multiple independent instruments and multiple spectroscopic analyses. The stellar masses are real. The distances are confirmed through independent redshift measurements. Webb has confirmed the existence of GS 9209, a quiescent galaxy that completed its star-forming life within the first 1.8 billion years of cosmic history, with a stellar mass exceeding that of the present-day Milky Way. This detection was published in Nature and has not been retracted or seriously contested. The Hubble tension is confirmed at greater than 5 standard deviations, a threshold that, in physics, represents overwhelming statistical evidence that the discrepancy is real. Webb's 2024 supernova measurements confirm the local expansion rate measured by the SHA-0ES collaboration. The two measurements remain irreconcilable within the standard model. The combined stellar mass observed in the early universe across Webb's deep field surveys exceeds Lambda CDM predictions by a factor that multiple peer-reviewed analyses have described as in significant tension with standard models. And the hints of variable fundamental constants, while not yet confirmed, are statistically significant enough that several independent groups are actively pursuing follow-up observations. What does all of this mean for cosmological model revision? Here is the honest state of the scientific conversation. Lambda CDM does not break down entirely. The cosmic microwave background still matches its predictions with extraordinary precision. The large-scale structure of the nearby universe, the distribution of galaxy clusters and voids, still broadly fits the simulations. Most of what we observe in the present-day cosmos is still well described by the model. But models are not tested by where they work. They are tested by where they fail. And Webb has found, with a precision no previous instrument could achieve, the specific places where Lambda CDM fails. The early universe is more massive than the model allows. It formed structure faster than the model predicts. It contains a galaxy whose entire life cycle compressed into a window the model says should barely be the beginning of star formation. And it is expanding at a rate that two independent confirmed methods cannot agree on. And neither answer fits comfortably inside the model's predictions. Webb was built to confirm the model. The first thing it showed us was where the model ends. Several serious theoretical frameworks are currently being developed in response to these findings. The most conservative involves what researchers call non-standard initial conditions. The proposal that the inflationary period at the beginning of the universe produced fluctuations that were not perfectly random, allowing faster growth of structure than the simplest models predict. This is the least disruptive option. It keeps the basic architecture of Lambda CDM intact while adjusting the starting conditions. A second framework proposes early dark energy, a brief burst of additional dark energy in the first 100,000 years of the universe that temporarily altered the expansion rate, leaving a fingerprint that manifests today as the Hubble Tension. Several research groups have built detailed mathematical models of this scenario, and it partially resolves the tension on paper. A third framework involves interacting dark matter, the proposal that dark matter particles interact weakly with each other, or with photons in ways that standard models ignore, potentially allowing faster halo formation and explaining the mass anomalies Webb is finding. And a fourth, the most radical, and the one that the variable constants data touches, involves the possibility that the cosmological constant itself, the term in Einstein's equations that describes dark energy, is not actually constant, that it changes over cosmic time, that the universe's energy budget has evolved in ways our current models don't account for. None of these frameworks resolves all of Webb's anomalies simultaneously. That's important to state clearly. The competition between them is active, ongoing, and unresolved. The data is real. The anomalies are confirmed. The question is open. Think about what it means that we are, as a species, only now, with instruments launched in our lifetimes, able to peer back to the first 500 million years of cosmic history. We have been doing astronomy for centuries. We built the most powerful telescope in human history and pointed it at the dawn of time. And the universe, rather than confirming the model we had built across 40 years of careful work, showed us something we don't yet fully understand. That is not a failure of science. It is exactly what science is supposed to do. The framework cracks precisely at the point where the instrument becomes good enough to see the cracks. And the researchers who spent their careers building Lambda CDM are, for the most part, the same researchers now doing the work to understand where it breaks and why. If you've been sitting with this data for the last 50 minutes and feeling the weight of what it leaves unresolved, that is the appropriate response. The scientists closest to this evidence feel the same weight, not because the universe is threatening or alarming, but because the honest acknowledgement of how much remains unknown is, in every era of science, the beginning of the next phase of understanding. We built the most powerful telescope in human history to find answers. The first thing it showed us was how many questions we hadn't thought to ask. And there is one question, the deepest one, that this documentary cannot answer. That the scientific community, as of this recording, cannot answer. And that may remain open well past the point where everything else we've discussed tonight has been resolved or revised. We opened this documentary with an image, a grain of sand held at arm's length, filled with thousands of galaxies, each one a city of hundreds of billions of stars. And with a question, what does it mean that the universe in that image doesn't match our best description of how it formed? An hour later, that question is larger, not smaller. We now know the anomalies are real and confirmed. We know the model is under structural pressure from multiple independent directions. We know the most likely resolutions involve adjusting something foundational, initial conditions, dark matter behavior, dark energy's constancy, or the assumption that the laws we measure today applied uniformly at the beginning. But the deepest question, the one that Loop C in this investigation points toward and cannot close, is this. If the early universe operated under conditions sufficiently different from today that our physical laws mischaracterize it, then what are the laws actually describing? Are they a complete account of nature? Or are they a precise but partial account, accurate within the epoch we inhabit but incomplete at the boundaries? The next generation of instruments is already being built to test exactly this question. The extremely large telescope, currently under construction in Chile, will directly analyze the atmospheres of rocky planets around nearby stars. And it will also resolve spectral lines in distant galaxies with a precision that may finally confirm or rule out variable constants. The CMB-S4 experiment will map the cosmic microwave background with 10 times the precision of any previous measurement, potentially resolving the Hubble tension definitively. The Nancy Grace Roman Space Telescope will survey vast swaths of the sky and provide the statistical dataset needed to test whether the galaxy formation anomalies are as widespread as Webb's deep fields suggest. That data will begin arriving within the next decade. When it does, everything we've examined today will either be confirmed, complicated, or overturned. That's the nature of this work. The universe doesn't wait for us to understand it before showing us something new. When we started this documentary, the question was what it means that the James Webb data shows a universe that doesn't match our best description of how it formed. We now have a clearer picture of the data. We have a more precise understanding of what is anomalous and why. We know the anomalies are real, confirmed, and not going away. We know the model that described the universe successfully for 40 years is under structural pressure from multiple directions simultaneously. And we have, if we're being honest, a much better understanding of how much we don't know. The title of this documentary is a question the data raises, not a conclusion it settles. Because in the end, the phrase impossible galaxies is not a claim about the universe. It is a claim about the model. The galaxies exist. They are real. The light that formed them traveled for 13 billion years before it landed in Webb's mirrors. What is impossible is not the galaxies themselves. It is accommodating them inside the framework we built before we could.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast. I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior, you know I'll always be a bit superior. Get off of me, this ain't no humble brag. I want you to hear words, you can say them back. I want you to feel free from the chains at last, and to believe in what you got, it was built to last, yeah.
Now that I've been put through hell, I never got anyone's help. I had to do it all myself.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Gonna learn the consequence of being incompetent. Mental health is confidence, dreams and some modestness. I'm not here to save the day, that's for you to take away. I could play a million mind games, but instead I say something not illogical, something that is topical. Rub it on and watch it go, make yourself unstoppable. Dreams are irresponsible, but they're always possible. If you just believe, you could be so remarkable.
Thoughts in my head, a collage and they spread. I'll be great one day, going off of my meds. No, I'm not giving up.